Kinect Software Systems, the company that myself and my partner Gordon Bell, both Waterloo graduates, formed, I guess, well, we actually incorporated the company before we left the university. We were, I guess, optimistic. And then we went to Bell Northern Research and we put in 2 years there doing what most people at B&R do when it still existed, work there for 2 years and form your own company. Initially, we developed an operating system which we called Q Unix, like Q with Unix on the end. And the company initially was called Quantum Software Systems. You'll notice a lot of physics terms. For example, the company was called Quantum. Our new microkernel is called Neutrino. We have a graphical user interface which we call Photon. But the lawyers at AT&T didn't like Q Unix. They thought that presented the wrong impression since we were not based upon any source code. And in fact, I have actually not looked at Unix source code. So they asked to change the name, so we changed it to QNX, which still sounded like Q Unix because we always pronounced it QNX. So people have often thought QNX stands for Quantum Network Executive, but in fact it's just 3 letters because we also recognized at that time that all successful operating systems had 3 letters in their name: CPM, DOS, and there were a variety of others. So today I'm going to talk a little bit about the embedded marketplace. I'll talk a bit about Internet appliances. Then I'm going to talk in a little bit of detail about our operating system, the Kinect microkernel architecture, because it applies directly to the marketplaces that we've gone in. I'm going to talk a little bit about Photon, our microGUI architecture, which is actually a windowing system based upon a microkernel, which I believe to be unique. And it's the one patent we've ever filed for. And then I'm going to give a demonstration showing how our architecture ties together to let you do things that most people find surprising, but in fact fall out of the architecture. When people do reviews in magazines, they always put benchmarks like, how fast do you context switch, or do you have this feature or that. But they always seem to miss the big picture, and the big picture is architecture. And we've always been really big in that. If you design an operating system and you get the architecture right, literally everything else flows from that. So, when you're at school here and you're learning things, pay a lot of attention to architecture. Don't look too at the details, look at the bigger picture. If I look at the entire marketplace, of course, at the top end, there's a server market, and it's got a small number of players. There's a desktop market, which is totally owned and controlled by Microsoft. And then there's the embedded marketplace, which is a completely fragmented market today. It's got over 80 different operating system vendors with well over 20 hardware platforms. To put this into a picture, on the one side I've got the mainframe, which is a market pretty much owned by IBM and Unix from companies like IBM, HP, Sun. And it runs on either mainframes or high-end microprocessors like Alpha, PowerPC, MIPS, x86, SPARC. I should have put SPARC in there, my mistake. And it's a market that is currently a growth market. If I move down a little bit to the desktop, it's a market that is completely owned by one company, Microsoft. It's an x86 only, there's no other viable processor, but it's also a market that has become totally saturated. And in fact, this is a market that is worse than saturated, because if you look at the list price of PCs that are going out today, if you're a hardware manufacturer in this market, it's a really scary place to be. The desktop marketplace has been a stable ecosystem now for probably well on 5 to 7 years, which means that when you went to buy a computer, you pay about the same this year that you paid last year or the year before or the year before, which is usually $2,000+. And the difference is that each year you buy a computer, you get twice the processing power, you get twice the memory, you get twice the hard disk. So what happens is your value, or what you're getting for your dollar, is going up, but the dollars are about the same. A company called Cyrix introduced a part called the Media GX about a year ago, which was a Pentium class processor that integrated onto the single die, not just a processor, they put a graphics display, accelerated graphics VGA within the same die. They put audio and a bunch of other things. And what that allowed them to do was to make a PC chip that sold for about $50 that could compete with low-end Pentium systems. And Compaq looked at this and they realized that the growth they needed was going to be in the sort of home space, not the business space, because they saw this tremendous potential to sell into homes. The problem they had was that most of the people that were buying computers had a price limitation. So they said, well, if we could bring the price down, we could open the market and sell more computers. So they brought out, I think it was called a Presario, which was a computer which they sold for under $1,000, which literally broke the model and the ecosystem that was out there. And subsequently, Cyrix got bought by National Semiconductor. And National Semiconductor is now saying that they're going to bring out what they're calling the cheap PC. And their goal is to bring out a PC that sells for less than $500 with Pentium class performance. If you go to Compaq today, you'd probably find that they regret ever having brought out that low-end system, because it's totally changed the face of the desktop marketplace. Because what it means is the profit margins are all gone. And if you look at the growth, something like 20% of the computer market today for the desktop is for computers less than $1,000. Within the next 2 to 3 years, that's expected to rise to 70%. What does that mean? That means that the companies out there who are selling these computers are now making a lot less dollars. And you're going to probably find a tremendous consolidation within the marketplace. And you're going to find that there's only going to be a few survivors. Companies like Compaq will probably survive because they have the purchasing power, so they can get their parts at, say 5 to 10 points cheaper than the smaller players. Companies like Gateway will probably survive, and Dell. There's an interesting story about National Semiconductor when it bought Cyrix. National Semiconductor's greatest asset is something very few people know about. Because of their growth from an earlier company called Fairchild, they actually have an agreement with Intel that happened with a patent dispute a long time ago that gives them the right to use every patent that Intel brings out to the year 2000, unrestricted. If you look at companies like Cyrix, when they were an individual, they always had to watch that whenever they brought out a clone processor, they didn't get sued by Intel, because Intel doesn't like people trying to follow too closely behind. The acquisition of National, of Cyrix, now gives them the ability to produce Pentium class processors without the fear of patent restrictions coming in from Intel. And in fact, some people at National said that was actually their greatest resource, was this patent that they were never able to capitalize on, for the simple reason that they didn't have the technology to actually produce the parts themselves. But the area I'm really going to talk about, though, is the embedded space. In the embedded space, there are lots of players. As I mentioned, it's a completely fragmented marketplace. We are one of the many RTOSs out there. It encompasses telecom markets, PDAs, set-tops, pagers, cell phones, industrial controllers, PLCs, a really wide variety. And the number of processors out there is also quite significant. The 68K is the traditional processor that had the strength there, but there's x86, MIPS, PowerPC, ARM, and Hitachi. And this is a really big growth marketplace. Now, looking at Microsoft, Microsoft currently has a total monopoly on the desktop. They are now seeking to extend that monopoly up with NT into the server market, and they're having a bit of difficulty currently because NT does not scale like the high-end Unixes. It is not as scalable a system. And they're trying to move down with the introduction of Windows CE. It's my belief, and of course I'm biased being a software vendor, that if Microsoft does succeed and grow and monopolize the markets at both ends, this is bad for the industry, because you will end up with a marketplace that becomes controlled by one company, which stifles innovation. So it's my belief that although I will agree that in the embedded marketplace there are too many players today, the last thing the world needs is to have a single dominant player that controls everything. Looking at worldwide shipments of RTOSs, it is a growth market, and from 1996 to early in the year 2002, there'll be about a 200% growth, and it'll represent about $1 billion. And this is conservative. In fact, I believe these numbers will be significantly higher. Looking at microprocessor use, you can see there's a large number of processors in this marketplace. And whereas Intel is king on the desktop, Intel is important in this marketplace, but they certainly don't have a dominant position. And when you look at price-performance ratios, if you're trying to build something in the area of consumer electronics where you have to shave every nickel, every penny, then Intel-class processors are potentially less competitive. Although Intel is addressing that. As part of this low-cost PC, Intel has recognized that that's where all the growth is going to be, and so they are now bringing out very low-cost versions of their Pentium processors with scaled-down capabilities. Mind you, if you look at Intel's revenue over the last quarter, I think they took something like a 38% hit, which is the first time that's ever happened to Intel. Again, recognizing that the heydays of the desktop are over. what it really means is everybody's going after the embedded market space, because that's where you're going to see literally hundreds of millions of devices popping up. VDC was asked, I went out and asked a bunch of people what RTOS they were using, and for some strange reason 10% of them said that they thought NT, or Windows 95, was a real-time operating system, and they actually represent the largest percentage of the market today. Unfortunately, the survey didn't include WinCE. The next surprising thing is proprietary operating systems represent 10%. That means operating systems that are developed within a company and never go any further. It's for their own use only. We actually come in 4th place if you ignore proprietary operating systems. Looking at this slide, from my point of view, the proprietary and DOS are actually, the fact that they've got such a good share today is actually good, because proprietary is starting to decline, because as the complexity of software is increasing, companies that have done their own operating system have recognized that it's becoming unmanageable, and in fact they're putting so much R&D trying to maintain their own operating system, they're missing their key competency, which is the product that they have to ship out the door. And as more companies move to 32-bit processors, they're shopping around for commercial product offerings. The really surprising thing about this slide is that 56% of the market is owned by companies that have less than 1% of the market, which just shows you how fragmented that embedded space currently is. I threw a Java slide up because everybody wants to know what's happening with Java. And this is, again, just forecasts. And basically it says that most people, or almost half, say that, yeah, they're going to use Java whenever they figure out what they can deploy Java for. 23% have figured it out enough to say, no, we're not going to do it today, and a lot of people just really don't know. Java's success is largely a reaction to Microsoft. It is an alternative. People want there to be an alternative, and it's my belief that Java will ultimately be successful as a language and as a platform. And our company, we've licensed both Sun's Java VM, but we've also licensed Hewlett-Packard, who have recently introduced an embedded. So we are licensees of both technology, targeting Sun's VM at the high end and HP's VM at the low end, because today Sun still doesn't have something which targets the embedded space effectively. So if I had to say what is the embedded market space, it's any system that is not a desktop business system. And that's really the best definition, stating what it is not. Because if you start trying to describe what it is, you'll be talking for hours. At the low end, or deeply embedded, you've got things like automotive control, which can be anything from engine control to braking systems, consumer appliances. At the high end, of course, you've got large industrial controllers, telephony systems, which may in themselves comprise smaller embedded components for embedded systems. Now, embedded and real-time go hand in hand. Whenever you see an embedded system, you tend to also see a real-time system. If you look at some typical applications, and these are applications that our product has successfully been used in. We're used in nuclear reactor monitoring, PLCs, warehouse automation, chemical processing, semiconductor manufacturing, plastics extrusion. This is sort of the old market of industrial control that we came from. We're also moving into markets like medical processing and instrumentation. And we've got systems where people are using our software for blood analysis, home dialysis. The interesting thing about the medical market is it's a great market to get into. It's really hard to get in because there are so many barriers, and they're looking for highly reliable systems. The good thing is once you get a medical customer, they stay around for a long time because the cost of re-engineering product and getting it through all the regulatory committees is so extensive that you get a customer on once that's medical, you've probably got them for 8 years. Whereas when you go into consumer electronics and internet appliances, the customer you had this month may be gone a year from now. Literally, there's, the rate of change is so rapid. The new markets we're going into is communications, which is switches and routers, telephony systems, which again is a huge marketplace. This slide actually came to me from one of the guys that who goes out in PRs, and he's got us under weapon systems. And to be honest, I don't know that we're used in any weapon systems anywhere. I do know that our software is used to make the wings of F-16s, but to my knowledge we don't actually run on any aircraft or any weapon systems. One thing I like to tell people, QNX, unlike some products out there, being embedded is not well known. One of the definitions are, if you go into the embedded marketplace, you might as well resign yourself to the fact that you're going to be invisible, because that's the whole idea of an embedded system. It's a fixed function or a system that does a certain thing and stays out of your way and is mostly invisible. You know, if you turn your VCR on, you don't want it coming up with a little logo announcing whose software is running inside it. You expect it just to do whatever it does. But most people in this audience, I suspect, probably interact with the QNX system almost every day of their lives. If not every day, certainly at least once a week. If you go to a Barnes & Noble bookstore, the point-of-sale system is all done with QNX. If you go to an ATM machine and you have to pull money from a bank that's not within the local area, it goes through a transaction system at Visa, which is done with our system. Just about every bottle manufactured in the United States is done using controllers that are run with our system. We were used in high security systems, home alarm systems, those big displays you see at a lot of sports events. Again, we're used within that. The entire flight control warning system of the southwestern United States is a large distributed QNX system. And lately, we've been moving into new markets for set-top boxes, web-enabled TVs, and smartphones. So the embedded marketplace really is a booming marketplace compared to the desktop, but it's got very different requirements. You know, as I mentioned, some degree of real-time control is required. Now, there's lots of definitions of real-time, and if you go to any university course, you'll probably get something slightly different. The one we like to use is a real-time system is one in which the correctness of the computations not only depends upon the logical correctness of the computation, but also upon the time at which the result is produced. Because if the timing constraints of the system are not met, system failure is said to occur. Simply said, it doesn't do you any good. The signal that cuts the fuel to the jet engine arrives a millisecond after the jet engine has exploded. Then there's soft real-time systems, which have reduced constraints, and this again is a really blurry area of whether you're hard or real-time. Getting into the area of internet appliances, there's really two classifications for devices that connect into the internet. You can classify them as client devices or server devices. Client devices are things like set-top boxes, network computers, web-enabled smartphones. The set-top box is a market that we jumped into about a year ago, and it had tremendous hype. The idea was that if you look at the number of people that are actually on the internet, it's actually quite small in relation to the entire population because you require a computer at home. So people said, well, what we need is everybody has a television, so what if we could put a little box on your television, connect it into a phone line or a cable modem, and let you surf the net on your television? And a number of companies, ours included, jumped into that marketplaces and people started rolling out products. Microsoft to date has spent $1 billion on this market. What people discovered was that, and it's obvious in retrospect, that people who watch television are not necessarily the same people who want to surf the internet. And it's because the media is completely different. When you sit down and watch television, it's a push media. Basically, everything's pushed at you. You just sit there like a couch potato and the stuff just flows by you. Whereas if you're doing something and you're searching for information on the internet, that's an entirely pull market where you actually have to engage your brain, you actually have to go out and start pulling things in. And so what they realized is these people sitting on the couch, they didn't want to do a lot of pulling, they wanted everything pushed at them. So what's happening is people are going back and they're regrouping saying, okay, people are not just going to go out and surf the internet, they need to have services, they need things pushed at them. And they're now talking about tying into advertisers such that you're watching a Toyota car commercial, you can click a button and maybe the web page of Toyota will come up, you know, which the advertisers love. You as a consumer may not actually think that's an advantage. And you know, having TV guides online such that it actually ties into your VCR, so you can on your television just look at the TV guide, select the pictures the programs you want to watch, and have your television automatically change channels at the proper time and turn your VCR on and off. Home banking is another huge application that the banks are very excited in pushing out, and which consumers are probably interested, where you can actually do some banking at home on your television set. That's also already available for people who have PCs. Network computers, Well, they were all the rage a year ago, but they're dead. I mean, network computers really offered two things to the marketplace. One, the cost of ownership of the device was less than a PC, which was like $2,000 plus, whereas the network computer was coming in around $500 to maybe $800. And then there was the cost of administration of a network computer. And if anybody's ever tried to administer a large network of Windows 95 machines, you realize the true cost of owning a computer. Our company has about 175 employees and about 350 computers. The guys in R&D tend to have 3, the guys in sales tend to have 1. And it's a major, actually the guys in R&D don't require a lot of administration because we run our own software, but it's a major administering Windows 95 with NT servers. What's happened is with the tremendous decline in cost of PCs going sub $1,000, potentially sub $500, that the network computer really doesn't offer a cost advantage purchasing it up front. And Microsoft finally is starting to acknowledge that network administration needs a lot of attention. So the cost of administration is going down. So most people who got really excited about network computers a year ago, IBM in particular, will now acknowledge, yeah, you're right, they're dead. It was a good idea, but it really didn't happen. In fact, it's interesting. When I went to university here, we had an environment where there were mainframes or big computers and terminals. Then the whole market changed, and what happened was everybody migrated off to standalone sort of computers where everybody had their own computer. Then they networked them together. And now they're introducing this concept of network computers where the computer becomes a terminal again, connected back to a mainframe. So here 15 years later, I'm right back where I started. The only difference is my terminal now is a processor as powerful as a mainframe I used to connect to, but I'm actually getting all my data and all my files reside back on a server just like they did the days I started. The other end of internet appliances is the server side. And this is where, rather than surfing out onto the net, you have people surfing into you. So the typical example being you take a small web server that can deliver HTML pages and you embed it in office equipment, vending machines. What does this mean? Well, this means that if I've got a photocopier or a laser printer or a fax machine and it's connected on the network, from my desktop I can target my browser at it and I can look at the toner, I can look at the number of pages, I can look at the service record, I can see how much paper is there. So it allows me, without any special software on the desktop, to go out and look at the devices. And this is a very fast-growing and exciting market. Those little digital cameras that you can now buy, initially, they had a proprietary communication protocol they used to deliver pictures you took in digital format that was on the camera and that would then be delivered back to your PC. Some of the new cameras are now going to put little HTTP servers in them, so in fact they're like little web servers. And in fact, all you have to do is connect your camera to your computer and you browse into your camera and it provides an HTML page with GIFs or JPEGs in it, which are the actual pictures. Again, a completely natural interface. In the case of vending machines, they tend to be both internet clients and internet servers. By that I mean that a Coke machine, you might want to go in and browse into a Coke machine to find out how it's doing. But at the same time, the Coke machine, if it starts to run low on Coke, might want to send out an email, which is a client device, to home base saying, more Coke please. So internet devices as clients require things like web browsers, plugins, emails, internet news, a bunch of things I've talked about. Live video when bandwidth is available. A lot of people got really excited about live video a couple of years ago, but the reality of the internet today is it is so congested and there is no guarantee of bandwidth that if you try to do live video over the internet at large, it's a very unsatisfying experience. The same thing is actually true for doing voice over the internet via IP voice for making long distance phone calls. I mean, the quality is about what Alexander Graham Bell probably had when he first started. But it is a market that will change as as the internet is upgraded and some of the new technologies go into place that allow you to guarantee bandwidth. Okay, I'm going to jump forward a little bit and talk about some stuff that we did. When we first decided to go into the internet appliance marketplace, one of the pushbacks we got from people was they had reservations of whether you could actually build a significant, meaningful rich experience in a very small memory footprint and with a very limited processor, because we're not talking about high-end devices here. We're talking about consumer electronics devices that typically, if they sell for much more than $300, you're in big trouble. So what we did is we decided to put together a floppy disk, 1.4 meg floppy, and we decided to pack onto it everything that would be suitable for a set-top box, showing that in 1.4 megabytes we could pack a desktop browser with full frames, animated GIFs, and all the features you'd expect, including JavaScript. We also put a tiny web server on board as well. This floppy disk contains our operating system, which is a full POSIX certified OS, which means it's a full Unix operating system, although it's not based on Unix source code. It's got a full graphical user interface, which is as capable and as extensive as Microsoft Windows or X Windows. We also threw on a small word processor, a file manager, a couple little games and demos, and we packed all that into 1.4 megabytes. And then we posted on our website for free download, and the results were absolutely amazing. We've now had over 300,000 downloads, and if you go to our website at www.qnx.com, you can download it yourself, either to a Windows machine, which will then let you cut a floppy because it downloads an image, or to a Linux machine, and you can cut a floppy from Linux as well. And what people found was they were absolutely astounded, because this isn't some cheesy looking browser that's all sort of black and white. It's textured buttons, and it looks really good. And people were astounded, and we've actually posted the comments of some of the responses we've got back, that in 1.4 megabytes you could run literally a Unix type OS, a full GUI, browser, the whole 9 yards, and fit it on a single floppy. So I would encourage anybody to go there and download it. I'm going to talk a little bit about our product, which has made the demo disk and everything that we've done possible. We are a microkernel operating system. What does that mean? Because just about everybody is claiming to be microkernel now, whether they understand what it means or not. The definition of a microkernel we have, it's a small piece of code that does a very limited set of functions. In Neutrino, which is our latest microkernel, it represents about 32 to 40K of code. If you think about it in its simplest form, it's nothing more than a software message switcher. Matter of fact, I try to do a hardware analogy, which is maybe bad in a computer science demonstration, but if you think about it, think of software modules like cards you can actually plug into a bus, and the microkernel implements a software bus. And if I want to add new capabilities, I can plug in a software module just like I could plug in a card that had hot swap. So I've got this Neutrino microkernel implementing the software bus. If I want to run a file system, say a CD-ROM file system, I simply start up a process that plugs into the bus, and it communicates with other processes via messages. If I want to start up a graphical user interface, TCP/IP, other file systems, everything literally just plugs into this bus. What are some of the effects of this? Well, first of all, you get dynamic configurability. Drivers are not built into the microkernel. All the drivers and interpandlers actually live out in user space, and the microkernel actually redirects them to processes. A process starts up, it takes over what we call a portion of the path namespace. It can take over interrupts if necessary, and then it starts to provide a service or a resource. We call these things resource managers. The effect of this is you end up with a completely scalable operating system where end users, not kernel guys, not us, can actually extend the functionality of the operating system without any source from us whatsoever. So for example, if you wanted to design a QNX file system, or CIFS, it stands for Common Internet File System, which is the Microsoft network file system they use between Windows 95 and NT. We actually call it crappy Internet File System, because if you've ever looked at the protocol, it's really bad. But if you wanted to write one of those, you write it just like you would write a normal application using standard compilers, standard user-level debuggers. You can start it up, you can take it down totally dynamically on the fly. So you end up with a system that allows you to reconfigure it or grow it dynamically while it's running. Each one of these processes lives in its own memory-protected address space. There are no drivers in the kernel, which means even if you have something like a driver fault, it doesn't take the system down. it will cleanly die and report back up to whoever started it that it's gone away. This allows you to build incredibly robust mission-critical systems. By using message passing, we also end up with the possibility for a distributed system. So, for example, let's assume that there's a guy there called Trace. Let's assume that Trace was just a user application. I don't know, let's say it's a text editor or something, and it wanted to open a file. The way it would open that file is it would send a message through the message bus to one of these file systems, who would then receive the message, and it would be an open message. It would then do permission checking, respond back with a file descriptor saying, yeah, you've got me. Then it would send read requests or write requests or various other standard requests. By adding one new process, which we call net, we merge all the microkernels together, and the messages can now flow off the local software bus onto the software bus of other computers. The net effect being that you now have a totally distributed system where a process running on any computer that is connected into the network can transparently access any resource manager, which means any resource anywhere on the network. And if you connect yourself into the internet, that also works worldwide. Now, we do a few things to make life a little bit nice. For example, if you have an application and it opens a connection, say, to a file system or some resource manager on your local computer, and the resource manager, and your application terminates without closing off its connections, the kernel guarantees that we deliver clean closes to the server. That makes writing servers easy. Even if the application forgets to do the closes, we do it for you. If the application dies because you wrote it poorly and it faults, you still get clean closes. Even if that application is on another physical computer halfway around the world, and somebody goes and takes a sledgehammer and flattens that computer, instantly you can be absolutely guaranteed that the server you wrote on the other side of the world will get a nice clean close message. So again, when you worry about details like that, it makes writing resource managers not something to be avoided, but something that is actually a relatively pleasant experience. If I look at the two pieces that I've shown, I've got the microkernel. The microkernel is responsible for a very small set of things. That's the thing about a microkernel. By definition, it has to be small. It runs in kernel space. It does thread creation, destruction, thread scheduling, thread weights. In fact, it's a direct implementation of the POSIX thread specification. We also have scheduling primitives for doing various scheduling algorithms, synchronization primitives like mutex and condition variables, signals and real-time signals, our own message passing, of course, timers so you can set up high performance timers, clock control, and interrupt handlers for interrupt redirection out into user space. By itself, you can actually link your own code directly against the microkernel, and you end up with what a traditional RTOS would be. A single process model with multiple threads living in it. So it's no memory protection, multiple threads using the services of the kernel as a single running image. That's not what we push, although if you've got a deeply embedded system, that might be what you want. By adding a process that, again, plugs into the software bus, we have something called a process manager. And what it does is it adds all the POSIX process semantics to the system, which are things like fork and exec and spawn, although it's not in Unix, it is part of a later draft POSIX spec. Path name management, and all the things that you would expect, and that enter shouldn't be there. Anyway, it adds all the process semantics, and now what you end up with is a system which consists of multiple processes, all living within multiple protected address spaces, each of which can be multi-threaded. What does this mean? From our point of view, it means we have an architecture which scales from tiny controllers down in the sub 100K byte range all the way up to huge gigabyte systems with SMP, because the neutrino kernel has been written to be SMP ready, and in fact it runs on Intel Pentium SMP systems. We call this the holy grail that a lot of operating system vendors are looking for. Most companies have one OS offering at the low end, something in the middle, and maybe something else at the high end. The problem with that is that if you pick one OS and you have to scale down or you have to scale up because what you're rolling out in an embedded system or you're rolling out into a factory floor needs to address higher end market or a lower end market, you suddenly hit these walls where the system you initially targeted bangs into something and you can't scale. What does that mean? It means you have to go to the vendor's other operating system, which they might claim is compatible, but as a general rule what you tend to find is they're not really compatible, and there's all sorts of little API differences, and in some cases they're completely incompatible. The advantage of a system like this is you end up with a single system, an absolutely consistent single API. All the binaries you develop run uniformly regardless of what's there. And not only that, but the system is completely scalable while it's running and is hot. If you try to look at the OS marketplace, there tends to be three models. The typical real-time executive model, everything lives in kernel space. The kernel lives there, applications run as threads within that space, device drivers, a file system, TCP/IP. A straight pointer anywhere means that the whole system will tend to go down. It also means that if you're writing application code in here, every time you relink the system, even though you made a very small change, everything could sort of slide around. So if you had a bad pointer someplace that was maybe pointing at an area of memory that wasn't really all that critical, you relink, you may be pointing in an area where damage can occur. So every time you relink the system, you literally have to go through a full QA analysis of that system, of all components, not just the tiny change you made. The monolithic kernel is the next model, which is what most modern operating systems use. And here they move all the applications out into user space, but they tend to still keep file systems, communication stacks, and device drivers in kernel space. To my knowledge, we are unique in the sense that we move everything out to user space, and the only thing that remains in kernel space is the microkernel itself. Now, resource managers I've mentioned are used for providing services like file systems, character I/O, networking, GUIs, and they can all be written by end users. They don't require any arcane knowledge of the operating system itself. They exist as independent memory protected processes, and they're totally dynamic. I mentioned Pathname Redirection. Here's an example where I've got a serial manager. When he starts up as a process, he actually registers with the process manager and says, I would like to take over the path names /dev/ser1 and /dev/ser2. Now any application that doesn't open of /dev/ser1 will have that open automatically directed to him. That's a name registry that's in place. We call it the path namespace, which is owned by the process manager, that allows people to connect to different things. And we also allow you to specify network IP addresses to go off node transparently to connect to a path name on a remote computer. We're also a hard real-time system. If you look at what happens in our microkernel, when a kernel interrupt occurs, we shut down interrupts on an x86 for about 8 opcodes. And at that point there, really anything happens with hardware, it's too bad. But 8 opcodes nowadays is like less than a microsecond. We then unlock the kernel, the interrupt system becomes fully enabled, and we're completely preemptible. Which means if an interrupt occurs and a higher priority thread should run, it will happen instantaneously, immediately. And that can take microseconds to milliseconds. Milliseconds would be in the case where you're doing a very long message pass. And I should probably make a little note here. Some people think message passing systems are slower than non-message passing systems. That in fact is not, that is a myth. And if you look at the performance of our networking, of our file systems, we match monolithic Unix systems and exceed it in most cases. And we still do support all the Unix POSIX shared memory primitives. A message doesn't necessarily have to contain all the data. It can actually contain the name of a shared memory region where the data is shared between 2 applications. So you can actually play both models at one time. At some point we lock the kernel down. Interrupts are still fully enabled, which means if an interrupt occurs at this moment, we queue the result, but we don't actually cause a thread switch or a preemption to occur. And that typically is a period of a few microseconds. We then unlock the kernel, and if an interrupt did occur, anything that had been queued we release at that point. And then finally, we shut down the interrupt system and return back to the now highest priority thread that is ready to run, which is typically not the thread that went into the kernel. I'm going to talk a little bit about Photon, which is our microkernel GUI. Oops, wrong way. We believe it to be the world's first and only microGUI. And again, it's configurable for small memory embedded systems, but it's also scalable up to large desktop systems. It's modeled after QNX. It's in the sense that there's a team of cooperating processes around a Photon or a graphical microkernel. And it too is network distributed. So if I looked at it, to bring up Photon on our microkernel operating system, the little yellow guy is actually the Photon microkernel, which is actually a process. You can plug in graphics drivers as processes, and you can have any number of graphics drivers. In fact, if you plug multiple video cards into your machine, you could have a screen that spanned all three of those. You could overlay them. Font managers, you simply drop them in at runtime. Window managers, input managers, everything is totally dynamically configurable. But I'm going to concentrate a little bit upon Photon, the microGUI itself. The interesting thing about Photon is that it doesn't know that it's a windowing system. It doesn't know a line from a circle. Has no idea that it's being used to implement a windowing system for the benefit of some user staring at the screen. What it does is it implements a 3D space populated with regions, which are created and owned by processes, and events, which are emitted into the 3D space by processes. Regions are simple rectangles, and events move through the space interacting with those regions. So here's a simple example of the 3D space where I've got the root region sort of stuck at the back, and at the very front, sort of closer to the user, think of it as closer to the screen, I've got a graphics driver region, which is owned by a graphics driver process who created that region. I also have an application who created a region somewhere in the middle of the event space. Events come in many different, there are up to 32 different events. We actually use a bit mask to determine, to categorize them. I'll get into that in a minute. One of the events is a draw event. So if the application wants to draw, it would emit a draw event within the 3D space, which would then travel forward, interacting with the regions that it encounters. And in this case, the only region it's going to encounter is the graphics driver region. So it'll hit the graphics driver. The graphics driver gets a copy of the event, which it then renders onto the screen or onto a printer or onto whatever. Regions have attributes. They have a sensitivity bit mask, 32 bits for 32 events, and a transparency bit mask, again 32 bits. The types of events are things like draw events, mouse events, keyboard events, expose events. And events are bidirectional. They either move from that root region forward towards the user or from the user back towards the root region. So things like keyboard events start out towards the screen, moving downward, trying to impact on applications, and draw events tend to originate from applications, and they move outwards towards the screen where you tend to put your graphics driver regions. If I look at a more complex picture, here I've got an example where furthest out towards the user I've got a graphics driver region. Then I have a keyboard region, which is injecting keyboard events. So I've got a little process that created a keyboard region and it's connected to my keyboard, and every time I type a key, it injects a keyboard event. I now have a mouse driver as well, which has basically created a mouse region, and it's emitting mouse events, all traveling in. This one called device, about halfway back, that's actually created by the window manager. And he is a focus region. And he knows which application or which region underneath them currently has focus. So when I type a key, he focuses that keyboard event such that it impacts on the appropriate application region at the appropriate place. So let's look at what happens with the four combinations. I've got a sensitivity bit mask and I've got a transparency bit mask. That gives me four combinations for each event. If I'm not sensitive and I'm transparent, then the event passes through the region totally unmodified. It's as though the region didn't exist. If I'm not sensitive and I'm opaque, which means I'm not transparent, then the event is clipped by the region, which means when the event hits the region, it gets clipped. And if it's clipped out of existence, because an event has an area, if it gets clipped totally, it disappears from the event space. If it's only partially clipped, then a clipped list is appended to the event, such as it moves forward, it continually adds to that clipped list. If I have sensitive, and in fact not sensitive opaque is what a normal application region would be to a draw event, because that way if I have an application underneath me who emits a draw event, I will clip their draw events, which means only the portion that I'm not obscuring will actually get through. Then I have sensitive and transparent, which means a copy of the event is passed to the region owner and the event passes through. sensitive means that you get a copy. So a graphics driver tends to be sensitive to draw events, but it also tends to be transparent, allowing multiple graphics drivers to all sit in the space at a time and all get a crack at looking at the event. And in fact, that's how we do a print screen. We simply have an application come up which creates a region way out at the front. It issues an expose event down, which impacts all the regions being clipped as it goes. All the application regions see the expose event. They redraw everything up, which then comes back to my graphic region, which then turns it into PostScript or Epson color, protocol or whatever, and sends it off to a printer or to a file or whatever. The last one is where you're sensitive and opaque. That means that you'll block the event, but you also get a copy. And that's great for creating filters. For example, let's assume I wanted to know what my application was going to look like if I only had 4 gray levels, because I was going to run my application on an embedded device that had a little LCD screen that only had 4 gray levels, but I'm running my application on a nice high-end monitor and I'm running 24-bit color. Well, I simply create a little application that's opaque to draw events but gets a copy. It sees the draw event comes in, it strips all the color out, reducing it to 4 gray levels, then it re-emits the event modified by stripping all the color information. And I can create a little application that I can drag around the screen, and it's a filter, and I can put rose tints and you can do glasses and green tints and whatever. But it's a way of transforming the event. And in fact, that's how we do things like handwriting analysis. We create a region up front which catches pen or mouse input. It sees raw mouse input coming in, which it does analysis on, then it modifies it and injects it as keyboard events. So you've got an application now, totally written by the user, nothing that we had to write, that is basically doing handwriting recognition, seeing strokes coming in from a mouse, so it sees mouse events, which it's sensitive to, but it's opaque to, and it re-emits keyboard events. So here's an example of event clipping, where you've got a region D that's done an expose, which has maybe done a draw, and what actually makes it to the graphics driver would be the draw event with a clip list broken down into 4 tiles. Okay, I'm not going to do a demo to try to put some of the stuff that I've talked about in perspective. That screen should have come live, but it didn't.
Here it is.
Okay. Okay, on the screen on the right is Microsoft Windows 95, I believe. And this is a Photon desktop. So it looks like a windowing system. It's got... if I can find my cursor here, I can bring up things like, a help viewer. And it does the sort of stuff you'd expect. We have nice opaque drag. We also have a virtual desktop manager, which means if I come down here, I can actually drag this into other windows. Actually, this is a little bit more obvious if I bring up a little world view guy. And now I can drag it into my virtual desktop. So in fact, I actually have, in this case, nine virtual screens that I can deal with. Oops. Now I talked about regions. If I go into development tools and bring up this, this is actually a view looking head-on of all the regions that are actually currently running within Photon's 3D event space. So if you look at it, I've got graphic driver regions, window manager, keyboard pointer, and that's sort of a view from the top being updated about once every second. If you want to look at it from the side, there's the same view, and you can see all the regions sort of living in that 3 space. So it's kind of a graphical view looking into the 3 space that Photon is implementing, which is the underlying pinnings of how we built this windowing system. And in fact, if I started dragging windows along, you should probably see some of those lines changing, yes, as things slide around. Now, I mentioned that Photon was a network distributed windowing system as well. What that means is that since all the graphics occur via message passing, and since messages are by definition network distributed, it means I could actually have two computers, and I could actually have the graphics driver on one computer and my applications in Photon running on a completely separate computer. The graphics driver does not have to run on the same computer as the application, which is actually good for embedded markets, because there are some pieces of instrumentation out there where they're saying, well, you know, I don't really want to put graphical hardware into my embedded system, but it's going to be on the network, so I'd like to be able to get at it from another system that does have all the graphics hardware. So you can actually deliver embedded systems out there, like maybe a telecom switch that has a completely graphical configuration, but there's no graphical hardware whatsoever on the actual switch. Well, as soon as you do that, the next question is, well, wait a second, does that mean I have to run a QNX system at the far end? And actually the answer is initially yes, but now no. What we've done is we've introduced a product that lets us export our graphics drivers actually across operating system boundaries. So let me bring up over here in Windows 95, I'll start a product we call Findos that will connect into this other computer. And actually I should probably describe, what I have here is two Toshiba laptops. One's running QNX, one's running Windows 95. Over here in Windows 95, I'm going to log in. Oh, log in as root, that'll probably work. Okay. And what I've done now is I brought up another desktop. What this really, all this really means is that this computer I have over here, this laptop, is now running, it's multi-user, and it's actually running 2 copies of Photon, 2 copies of everything. Of course, we share code. So QNX itself, by definition, is a multi-user system capable of hosting multiple users and multiple GUIs all at the same time. So it's like I have 2 users here. So let's assume that I'm working with somebody on my network, and I'm working with my help viewer here or whatever, and I'm talking to somebody on the phone, and they say, well, could you show me what you're looking at? Well, we have a little application here which we call the jump gate. If I click it, and it becomes active, I can now click on the application here. Wants to know what node I want to transport it to, and oh darn, I forgot my node number. Just a second, I'm not. Just a second. I'm node 269, okay. I actually have 2. If you look there, you have actually seen Photon running right. So it's 269. There's 2 people actually running, and the one I want to transport it to is this one. And what I've done now is I've actually transported the application from the graphical user interface on QNX over to the guy sitting who knows where on his Windows 95 machine. And now he can interact with it whatever he wants, and when he's done, his little return arrow hits a button and he'll return it back to wherever it came from. We have a nifty little application we call the Notepad, which, if I can, oops. Right here, which is basically a little sticky note. And what it does is it lets me type stuff in here, and I can write a little sticky note for somebody, and then I can transport it to somebody else's computer, and when they come back from lunch, they'll have a little yellow sticky note sitting on their screen. And it's not uncommon at our office to come back and have a couple of sticky notes setting up. You can then type in your answer and send it back. And so it's kind of like mail, but it gets more in your face because it actually leaves little post-it notes on your screen. So I've got transporting, and of course there's something else I could do. Let me get out of this over here. I'll shut down this version of Photon. I brought a shell up here. I can bring it up again. Sorry, I'm having trouble finding my mouse. It doesn't track very well on this screen. I don't have an active matrix screen. I probably could see it better if I looked up there. It tends to dive and disappear. Okay, there it is. If I bring up my shell, if I type ph, which starts Photon, I can actually type ph inside a shell window and bring up Photon inside a Photon. And hopefully it won't make me a liar because it's not starting for some reason. Well, I guess the demo god got me. It had an error of some sort. Didn't like. Well, we won't do that one then. Okay, over here, what I showed you was bringing up Windows. That's where I created a whole new Photon session on the QNX computer and connected it up to a remote graphical user interface, which we implemented in Windows 95. There's nothing stopping me from creating a graphics region that overlays the same event space or the same Photon that's running on this, which I can do with this one right here, at which point I get a ditto. So now in Windows 95, I literally can use either mouse. The mouse on this computer works, the mouse on this computer works, and you can have multiple people go in and ditto itself, and I get automatic collaborative computing. The important thing here is this all falls out of the architecture. There's nothing special here. We didn't actually have to go and think really hard to develop, special code. It all comes back to architecture. You get the architecture right, really hard things become really easy. Now, sometimes people don't want to bring up whole desktops, so in fact we let you bring up single applications. And no, didn't connect that time. I'll do the Windows side by side. This is one that's actually the most fun. What I've done in this case is I've actually started a graphics driver on the Windows side, and I've said rather than put it into its own space, or rather than put it on top, put it off to the right. So let's pretend that I have a viewable space that is across two computers. What does this mean? It means that I can now take an application and literally drag it right across an operating system boundary. And that's interesting, but what shows you the sort of performance you can get, this is a 10 meg Ethernet, by the way, connected between the two, is let me go to Demos and Games. And let me start up something that we ported to QNX a couple of years ago. So I've got Doom running here, and Doom, if you think about it, usually expects to write to a local frame buffer. It's basically writing right into a frame buffer, or under a GUI it's writing using the fasted method to put an image up to the screen. I can grab Doom, keeps going even though I'm smooth scrolling it, and I can drag it such that half is on one computer, half on the other, going across a 10 megabit Ethernet link. What's really interesting about this is that if this was it runs pretty fast for 10 megabits. If this was a 100 megabit Ethernet link, the game speeds up. Because what happens is the speed of the network link is no longer a bottleneck. The computation is done on one computer and the display is done on another. So you actually get parallel processing going on where you're generating frames in one and displaying them in the other. Again, you get your architecture right, this all falls out. In fact, when we started to design the operating system, the initial work actually came out of my hanging around the Thoth lab, where they were doing research on microkernel operating systems, although they didn't know enough to call them microkernel because nobody coined the name. And the thing that was really obvious was that if you're going to go out and design an operating system, the worst place to start is say, okay, I need a file system and I need some sort of device driver for this. You start off by saying, think of an architecture where you can communicate. Solve the communication problems first. Get a clean, extensible communication model. Make sure that it's network distributed, and then build everything on top of that. So Neutrino as a microkernel is really nothing more than a framework of communication that lets you build whatever operating system you want. In the case of Photon, whatever windowing system you want. That's most of my talk, but there's a few things I'd like to say. When I left the university, geez, it was a long time ago, but I was working on what became QNX way back then. But when I first left the university, all the work that I was doing was done on a mainframe you had here, which was a Honeywell 6660, I believe. And I had built my own 6009 wire-wrapped microprocessor board, and my partner Gord had built one using an 8088. Actually, we always battled. I always said Motorola would win, he always said Intel would win. Then IBM introduced the PC and I lost. But I'm getting even because we're going multi-platform. We're going back to PowerPC and MIPS and other processors. Anyway, the important point was that when I left the university, we were not self-hosted, which means that the compilers and the editors and all the stuff that we wrote while at the university didn't run locally on our own little tiny microcomputers. It only ran on the Honeywell. And I graduated, and both of us headed back to Ottawa, and the university held my account open for an entire year, although I was no longer a student. And they actually did a lot more than that. They gave me data pack access, which means I could dial a local number in Ottawa and connect into the Honeywell so I could do my downloads, which were 300 baud in that days, to download images of stuff I compiled to make myself self-hosted. And considering I was probably on 40 to 50 hours a week, and knowing what the phone company used to charge back then, Kinix and my company would not exist if the university had not done that. Now, I never exactly knew who to thank, but I suspect it was either Peter Fraser or Preston Gerd that was involved at that time. And I just wanted them to know that if indeed you played a role there, which I believe you did, that I would not have existed if you had not done that. And I'd like to make another offer right now. We have a full, exciting, I think, research class level operating system called Kinix. It's a full POSIX implementation. We have GUIs, we have tools, we have all sorts of stuff, which we package on a single CD-ROM, and if you added up the retail price of it, it probably comes between $5,000 and $10,000. I would like to state now that I would like to offer to every student within this university a copy of that CD-ROM at no charge for the life of my company. So I will be contacting the faculties, and anybody who's interested in receiving the software, I will be making it available to the university, no questions asked, no limitations, for everything that is in my power and that I own and I control. So, and I hope you have as much fun with it as I have. And one other little thing, when I first started Kinix Software Systems, which is actually called Quantum back then, I was pretty naive, as I think a lot of people are. I was full of passion. But you're at the best university you could possibly be at, and you're taking courses that are necessary and essential. But it's important that you do stuff outside your courses as well and find out what it is within this field that interests you and excites you. And those passions really are important. I mean, I am here where I am today because of what I did beyond what the university gave me the framework and allowed me to do. And I know that when I go out to hire people, I look for people who have that passion and that excitement. People who get up in the morning, and what I say to everybody when they come to the company, I said, every morning you get up and you come into work, ask yourself, do I enjoy doing this? Because if you don't, for God's sakes, get another job, because it's at least 1/3 your life. It's half your waking life. So it's important that whatever you pick in this field, that you apply yourself and you generate excitement and passion in doing it. And wherever you work, make sure you work for a company that appreciates that and gives you back the, what is necessary to allow you to grow and to express yourself. And I've tried to build a company like that. And it has been an incredible ride, and I can't imagine myself doing anything else. Anyway, thank you.
Take questions, Dan?
Oh, right.
We have some time for questions, and I'm sure Dan would love to answer some questions from the audience. I personally want to thank Dan for his most generous offer. I just takes my breath away, so what else could I say about that? Questions from the audience? Who wants to go first? Oh, there's lots. So, Dan, I'll let you field some questions.
When did you figure out you went in the other market?
Well, it's interesting. We decided very early we were not going to go into the desktop market, which is, I Some other operating systems actually came out of Waterloo, targeted that space. We decided to go after the real-time space quite early. And initially, we went after sort of the process control market, which is an embedded marketplace, but it's really built upon sort of PC infrastructures and PC chassis, or perhaps hardened PCs. And that was a market that was quite good for us. But Microsoft started moving into that market with Windows NT, and it was about 2.5 years ago that we decided that the market space we wanted to go into was much deeper. We wanted to get into the telecom market, and it became apparent that the reason we were winning sales was because of our architecture, the fact that you could build fault-tolerant, highly reliable distributed systems. And so that's where we started to focus. The embedded marketplace for consumer electronics is a marketplace that is exploding. It's one that we couldn't ignore. And Photon, to be quite honest, was a complete fluke. We had actually licensed a windowing system from another company in Toronto, and we were dissatisfied with it. So literally it was a couple of guys up in R&D, one guy that had been there for about 2.5 years, and one guy who was a student that was in grade 11. And literally, it was the two of them that thought up the concept of building a windowing system based upon these simple principles. And they came to us and they said, can we pursue that? And we said, absolutely. And so we let them play for literally about a year doing research on it until they brought their first prototype up, and then we moved forward from then. And Photon has been an absolute differentiator for us in the marketplace because it allows us to build, Photon itself runs with a full widget set, which is things like divider widgets, folder widgets, combo boxes, tree widgets, comes in around 500K. So it's quite small. And if you strip the widget library down, the Photon microkernel itself is about 40K. So Photon is what has allowed us to go into point of sale, medical instrumentation, and now into the internet business. And we licensed a browser off a company called Spyglass, which we have subsequently severed the links with Spyglass and taken over the code ourselves because we've applied over 2,000 bug fixes. But it's very solid now. And we've actually gone after that market. And from the set-top box, we were disappointed in the sense that we signed up a number of major companies. Philips is actually introducing a set-top box in the Asian marketplace based upon our stuff. They sell web TV in North America, but they sell our stuff over there because we have a lot more performance, a much smaller memory footprint, and our licensing costs are significantly less than Microsoft. And France Telecom recently picked us as the winner of a trial of several systems over there for a potential replacement for the Minitel. In Norway, a company called PCTVNet is getting ready to launch a system. There's a company in the United States that initially called Neon that launched a system, but it was not accepted as well, so their sales are way below what we would have liked. The set-top market will be successful, but it's just going to take a lot longer than anybody anticipated. And ultimately, it'll roll right into your television, which means it won't be a separate box. It'll just be part of the TV that you buy. It'll be like picture-in-picture. It's a feature. So when did we ask to go to the embedded space? I guess we've always targeted the embedded space. We only started saying it strenuously in the last couple of years.
I was wondering where you think research in this area should be going in the next 5 to 10 years.
Well, when we did our first microkernel, which is called QNX 2, we thought we knew it all. And then we did QNX 4 and realized that we were idiots. And then we've just done Neutrino and realized that, boy, we didn't know anything with QNX 4. So the thing about doing research into microkernels is there's a certain elegance in the architecture. There's a real balance of deciding the responsibilities and functionality that goes into that as opposed to what gets moved off into sort of user space. Because there's a huge performance difference. And if you make the wrong decision, you limit your architecture and you limit your performance. And we've gotten better at it every year. I think there's a lot of work that could be done in fault-tolerant distributed systems because although we have the underpinnings to allow you to build them, that's not actually what we ship out the door. For example, we, in our networking, allow you to plug multiple networking cards in, and you can connect them with multiple cables between multiple machines, and our network manager will automatically sense that if one line goes down, it'll switch over to another line, it'll load balance. There's a lot of research and a lot of things we could learn because the initial stuff we did was for low latency networks. When you start getting into the internet, which is a high latency network, the whole message passing paradigm changes substantially. And there's a lot of research that can still be done in message passing over large, distributed, high latency systems. When you're talking about performance, there's a lot of research that can be done in MMU and cache design. One nice thing about a microkernel is it's small, which means it doesn't tend to flood or overflow the cache, causing pages to be flushed out. So that's another nice thing about a microkernel. If you've got a small amount of code through it, it tends to live in the primary L1 or L2 caches, which gives you a natural performance boost, whereas if a large monolithic system with code all over the place, you tend to, because of the, the way the caches are set up, you tend to be throwing out hunks of code that you're just going to return back to quite shortly. So I'd say if I had my druthers, I would want to be doing in our company a lot more research into building reliable, distributed, fault-tolerant systems. I do a lot of research in fine-tuning the internal architectures for performance. And in the area of Photon as a microGUI, we've hardly scratched the surface of what it can do, because it's a whole new field. And it's the only patent, again, our company's ever applied for, because we felt it was, although hopefully when I explained it, it makes sense and is easily understood. Nobody else, that's the best patent, of course. I've never seen anybody else, look at it that way.
How specialized is Unix development?
Currently, we use the Wacom compiler set, but QNX 4, we're going to shortly be shipping standard GCC. And how specialized is it? Initially, QNX 4 used our own load file format. We're going to standard Delft Dwarf everywhere, which means that we will look just like any other Unix. Neutrino was like that today. We actually have two products. We have QNX 4, which is sort of our desktop product. We have Neutrino, which we're still targeting at that small embedded space, but which is growing up real fast, and which will go well beyond QNX 4. It's scalable from little tiny systems to those big SMP systems. Probably by early next year, Neutrino will be the premier OS that we ship out the door, and it will be a full Unix-like system. For example, if you look at the Apache source code, which is probably the most popular web server out on the internet today, huge bundle of source, bring it onto your QNX system, type make, and it just works. So if you're used to Unix, you'll find that Neutrino, or QNX, or /QNX Neutrino is, well, it's a POSIX certified system, so it looks like a Unix or a Linux. Yes?
What, if anything, can Windows systems or Unix systems of today do that you can't do? And if there isn't anything there, what stops somebody like you from producing a converter that converts applications in those areas to run on your system?
Well, what we have as an operating system is far more capable than Windows 95. It's far more scalable and as capable as Windows NT. There's absolutely no question about that. What we don't have is we don't have the application base. In the big Unix area, we don't have ports of most of the big servers, although we do have Sybase, which is excellent. We don't have all the desktop word processors. We don't have, it's mostly an application thing. And even if we do have the underpinnings, QNX would make a wonderful desktop operating system. There's no question about it. I mean, you try to run Windows 95 and you get a few things going in the background and it becomes unbearable. Your cursor hardly moves. I can bring up multiple things all going at once. It's multi-user. It's real-time. It's deterministic, multimedia, the whole 9 yards. But Microsoft virtually owns mindshare and market space. It's unfortunately what you will learn in the real world. Technology may get your foot in the door, but it really only is maybe 30% of the equation of actually being successful. As for doing converters, Microsoft has produced so much code with such incredible complexity, none of which is properly documented or standardized, that to try to clone those interfaces would consume any company. And virtually, if I tried to start chasing Microsoft or trying to clone their APIs, I would probably be bankrupt and exhausted within a year or two. So what I've done is I've struck off on my own and provide an alternative. We do actually have a Win32 subsystem, which we licensed from a company that implements the full Win32. So you can take any Win32 application, you can compile it in our system, and it'll just work. But guess what? It's useless. Because how many Win32 only applications are out there? They all require things like Microsoft Foundation classes. And guess what? You can only get that from Microsoft. It's not available, certainly not to myself. So all the big application builders that people use out there use DLLs and code which I have no access to. So yes, if you write everything in Win32, you're fine, but the reality is almost nobody does. They use higher level toolkits to produce stuff that I can't get. I mean, we have our own application builder, which is, if I can find my mouse again. Anybody see my mouse? I've lost it on this. Should have got an active matrix display. Where did it dive down to? Top right? Oh, sorry, you're right. It's on the other computer. Sorry, I forgot that I joined the desktop. Okay. Okay, this is actually an early version of FAB. The new one is a lot cooler. Oh, and it's actually interesting. FAB came up and asked how big the screen was, and it's been told that the screen is actually this wide, 2 times 800, 1600 pixels wide, because in fact it is. It's got the full 2 screens to drag over. And, you know, the new one's a lot fancier than this. This would also be part of the package that everybody would get. Actually, I wonder if we've got any examples here. No, unfortunately I don't. I tried to center it so it's centered across my 2 screens. No, I don't see any applications / user Photon. Nope. I don't have any apps on this system right now. They just installed it. But it's a standard GUI, you know, drag and drop tool. I can grab things like, you know, combo buttons. I can bring in, you know, I can drop in a list. Oops, I guess I should have made it a little bit bigger than that. Oops, didn't get it. There's scroll bars and areas, and we have HTML widgets you can drop in. You can drop a terminal widget in, so you can bring up a terminal rate in it. You know, it's what you'd expect from a very high-level application builder tool, which we call FAB for Photon Application Builder. Hey, let's save changes. No. Okay. Yes?
You have a Java virtual machine running QA.
We have one underway. We have the Sun VM, which we've licensed, and we are currently porting the Hewlett-Packard embedded VM. And when I left, they received the source code on Monday, and they had it compiled and linked into a module on Thursday. Actually, Thursday when I left. But they hadn't started testing on it yet. I expect we'll probably have it up and running in-house within another week or 2. Yes?
When you port an application to Unix, what kinds of re-engineering do you need to optimize it for the real-time multi-thread distributed thing? Because maybe an architecture written, process something, maybe do it very efficiently.
Well, the nice thing about it is you really don't have to know too much about that for most things. I mean, it's not like you actually have to send a message to open file. You just call open, and we provide library routines that marshal your parameters into a message and do that all under the covers for you. We have all the standard POSIX real-time specifications for timers and semaphores, mutexes, and all that sort of thing. If you have an SMP system, we're very careful. We make sure that our mutexes and semaphores and condition variables work, of course, in an SMP environment. But we've actually gone beyond that. We even make sure that we have interlocks that work between an interrupt handler and a thread. Because on a single machine, you could make a thread or a process running, and an interrupt handler goes out. The interrupt handler can usually be pretty sure that it will not run at the same time as the process because one preempts the other. In an SMP system, your interrupt handler could be running on one processor while your thread is running on the other. So we've actually made sure that we have standard primitives that users can develop. And unfortunately, this is not in the POSIX spec, although they're talking about these in a draft spec that allow you to do things. We've been really careful. I'm going to make an announcement in San Francisco on Monday that although we have been an x86 only company for 15 years, we are going multi-platform with Neutrino, and we'll be supporting a wide variety of processors, initially MIPS and PowerPC. And we've been careful of that as well. When we develop a device driver, it's all developed in C. When we go to access a register or a port, we surround it with a macro, which comes from a file called gulliver.h, which deals with Indian issues. The people here know the Gulliver joke about Indian? There's a story that in Gulliver's Travels there was this big discussion of whether the big side of the egg should be up or the little side, and it was like the Indian, which end? Well, if Indian in microprocessors tells the way the bytes are laid down for most significant to least significant, or least significant to most significant, and although it sounds trivial, it causes tremendous grief to people who write device drivers. We've developed all our drivers in C. We use standardized macros to remove Indian issues and alignment issues, and we also have a standard set of macros that make the I/O space independent. Because on an Intel processor, the way you read registers for hardware is typically using in and out opcodes, whereas in something like a PowerPC or MIPS, it's usually mapped into the address of memory space. The net result is that I can show you an Ethernet driver that runs in MIPS, PowerPC, and Intel. It's source code identical. The driver is totally unaware of what processor it's running on under the covers. The same is true for our communication driver, the 8250. We decided to solve these problems with architecture up front because too many companies have been destroyed by going wide by supporting a lot of processors and being absolutely killed by doing board support packages and drivers that have to be replicated for every processor and every board. And in fact, the kernel itself is completely board independent, which means the kernel itself is identical on any MIPS board that you run it on, whether it be a MIPS 4300, a 4102, a 4000, or a 5000, the kernel is identical. The same is true for PowerPC and all these. And the way we do that is we have a little tiny piece of code that we provide in source code form for the user, which we call startup. And what it does is it exports just enough code for the kernel to do out calls back to remove all hardware dependencies. Hardware dependencies that a kernel needs to know about are things like timers, because it needs to know about real time, how to handle the interrupt system, how to end an interrupt, little things like that. And so the net result is that we've ended up with one kernel that works with every MIPS processor, one kernel that works with every PowerPC processor that we've tried to date, and that includes IBM's 401, 403, Motorola's 860, 821, 823, and the same for MIPS. Again, you take your time and you do it right. If you do it right the first time and get your architecture, then you'll save yourself untold aggravation in the future. Actually.
What are Unix's strengths over VxWorks and vice versa?
It'll take me a second to think of a strength for VxWorks. VxWorks is basically an architecture that grew out of real-time executives that were developed for the 68K with one flat address space. They have no process model. No process model whatsoever. All they have is a thread model. If they tell you have a process model, that is not really true. I mean, they may pretend that they're loading processes, but you look at a fork or something in VxWorks and see just how well it works. Most of their systems run in a common address space, no memory protection. They have these extra things that sort of let you protect the space, sort of like you can protect your code, but you can't really protect your stack. If you look at Wind River and Integrated Systems, which is PSOS, and most of the other companies out there, they come from a very early history where all their OS offerings are similar. And how they decided to differentiate themselves was with tools. And you could look at the companies. They brought out high-end development systems. Wind Rivers calls theirs Tornado. I think Integrated Systems, they call theirs Prism. So they differentiated themselves and they poured all their energy into tools. And in fact, I probably shouldn't say this, Wind River flew up to talk to us 2 years ago to try to acquire our company because they said, we don't have a process model. We don't have the level of OS technology that you have. We've done nothing on our operating system for about 7 years. And rather than starting over again, we would like to start off with what you have and move forward, and we said no at that time. So Wind River as a company has been very successful. I would say they are number one. They own the embedded space today. But that was when I was on a single processor x86, which really has never been in telecom, although it's starting to show a presence there. And although I see Windows CE as my ultimate competitor, Wind River will be the first company that I probably come in direct confrontation with as I move into their space and their processors. In fact, a scary statistic that I saw a couple of months ago was when a project is started, what do you pick first? The processor and the hardware or the software? And I think the number that came back was something like 72% picked the hardware first, and something like only 16% actually picked the software first, which means that I've actually lost before I even get my foot in the door by restricting myself to a single processor, which we're going to change. So from an architecture point of view, Wind River would be that monolithic real-time executive. There's a world of difference between our two systems, a world. I mean, you try to grab something like a huge hunk of source off the net that's designed for, you know, a proper POSIX process model and try to get that working under Wind River, and you're probably in for quite the task.
Any more questions?
Okay, 2 there.
Well, the Intel x86 architecture is certainly not the one I would have chosen first for anyone, except for this market penetration. Now that you've run on a number of processors, can you tell us which of these processor architectures you find most conformable to your system?
We like MIPS. We like the fact that it's got a software TLB. It gives us a lot of flexibility. It means the cost of a context switch from a process to a process is less dramatic than in an Intel processor, where you pretty much have to throw away the entire TLB. So, so far the guys that have been working in the kernel like MIPS the best. PowerPC is okay, but the thing with PowerPC is we think they murder every engineer that works on one part so they can bring guys in with fresh ideas who decide to move bits around in registers and redefine. It's just, it's really frustrating. So yes, we have one kernel and they make these subtle, unexplainable changes from the 401 to the 403, and it's like, why did they do that? And we find that a little bit frustrating. So right now we like MIPS a fair bit. Although it has, the MIPS has a virtual cache, which would make it a poor choice if you wanted to do an SMP system. It would be quite complicated. x86 at least has a physical cache, which makes SMP support much easier, at least from a software point of view. And we haven't ported to ARM or Hitachi. We're just starting to look at those ports. The next port we will probably do will be strong ARM, and that's because when Intel bought Digital Equipment Corporation, the semiconductor side, they got the rights to produce strong ARM parts. And I suspect that Intel is going to come out of the gates and make some major announcements in the coming months where they're going to position strong ARM as their embedded solution, because Intel has been sort of caught off guard. And what's happening is the desktop market is sort of, you know, saturated, and they're looking to move into these new markets. And they don't want to sell Pentiums for $10 because they want to sell them for like hundreds of dollars on the desktop. So they can introduce a new part that would be good. And their 860 and 960 are pretty well dead. And there was,
The last sentence I missed.
oh, they have two other processors. The 960 is like, you know, it's a dead part.
Last question?
So you rely on, within an architecture, you rely on compilers for any optimizations for a particular process?
Absolutely. Yes. And in fact, the proof of that was we had a floppy driver written entirely in assembly language. We wrote it in C and fed it through Wacom's compiler, and the byte count went down. So it did a better job of optimizing than the guy that did the assembly, because as soon as your code gets to a certain size, a good compiler can do a much better job of global optimization. So yes, we rely relatively heavily upon the compiler to do a good job. Although in the case of the graphics drivers, we still tweak, you know, blitz and, you know, and images and stuff like that. There's always a little bit of assembly, but minimal. Oh.
Well, again, I want to thank Dan for a very enjoyable talk. I found his enthusiasm very engaging. It's obvious that he has a passion for his work and for his company. And I'd just like to show our appreciation to Dan for coming today.